go back to what we learned last time, right? Every time you see a circuit, the first thing ask yourself what type of circuit it is. Now, do you know what type of circuit this is? Without looking at the title. It's a,
Didn't mention.
you won't pay attention, right? So this is very important. That same problem for me. Always look at the title when you read a paper. I always spend a lot of time to understand a circuit without realizing that it is in the caption and the title. Really, that saves you a lot of time. So it is Cascode, and why? Because the input is here, output is here, and then the first thing you think, oh, that might be common source. No, but then the output is not at the drain, right? Because it go through the source, which is constantly biased at the gate of another transistor, and then you go to the output, right? You should recognize this device right away, right? So we talked about Cascode circuit last time. And in order to find the poles, right, again, we start with zero bias, with low frequency, and then go to medium frequency, eventually go to high frequency. At high frequency, we care about these parasitic capacitors, right? So last time we said we have 4 transistors, so 2 transistors, so how many capacitors do we have? 8, right? And then we try to simplify them, and then we apply the Mueller effect for simplification. For example, if you remember, one of the capacitor must be this one, which is CSB, right? But both of them are grounded, so no use, right? No effect to this transistor, to this circuit. And we also apply the so-called Mueller effect, right? The most important Mueller effect is which one? There's only one, actually, CGD1, right? This is the capacitor that has one terminal connected to X, another terminal connected to Y, right? And we cannot apply the inspection method that we have been using. We always say that I stand at X and then ask what is the impedance that can bring me to ground. I need to ground V in, right? Because it is independent. So I say, oh, it is RS. So I have RS here. But then what is the capacitor that can bring me to the ground? Well, I see CGS1 because I do have CGS1 here. But then I also see CGD1. But however, this is not grounded. So I need to apply the Mueller capacitor, right? And to apply the Mueller theorem, I use this theory, right? I say that if I have a capacitor here, and it gives me a gain of A from the left terminal to the right terminal, then this capacitor will be decomposed into 2. I can decompose it to 2 capacitors. Do you remember what they? What's the one on the left? CF 1 minus A, right? Very good. And how about the one on the right? Very good, yeah. CF times 1 minus 1 over A, right? But the main question, the most important thing is, what is A? Again, A is the gain from one terminal to another terminal. So what is the A for this one? Is the gain from X to Y, not the gain from X to V out. Yeah, the gain of your whole circuit is from X to V out. Very large, GMR square, right? GM square R square. See, when you simplify for Cascode. But from this point to this point, it is pretty small. And what is that? Do you remember? Although the answer is here already. Yeah, but why it is GM1 times GM divided by GM2? Maybe someone just say it, right? We studied last time. Anyone remember? Why the gain from X to Y, not from X to V out, from X to Y is GM1 over GM2? Again, the gain from X to Y is the gain of what type of amplifier? Huh? I mean, what type of amplifier? Common source. Right? When I ask the gain from X to Y, it is the gain of common source. It's okay, you don't know how to calculate it, but you should know that it is the gain of a common source. Right? Because I'm talking input is X, output is Y. Isn't that is the gain of common source? And what is the gain of a common source? Say again. GM1 R out. Let me call it RD. Okay, a common source, right? Negative. Okay. What is RD in this case? Right? If I treat this as an amplifier, what is RD in this case? 1 over GM2. Why it is 1 over GM2? Because you're, say again, into where? Into the source, yes. So that's why I need to slow down, right? So very good, because you look into the source, right? This part, you look up, and you already solved this or see this in the assignment many times. It's the input impedance to the source of the common gate amplifier. So it's 1 over GM2, right? So that's why the gain A is negative GM1 divided by GM2. So that's why CGD1 becomes CGD1 times 1 plus GM1 divided by GM2, which is small, right? Because GM1 and GM2 have the same order of magnitude. So maybe about, this is almost equal to 2, maybe 1 plus 1. Is this okay? Yeah, so with this, then I get the pole RS times CGS1 plus this Mueller capacitor. And I do something similar for the rest, then I will get this pole. Okay, so that is a review for what we did last time. Any questions? Right, and you know that for midterm and final, what I'm giving you is should not be more difficult to what we study in the lecture, right? Yeah. Yes, I'm very good. Thank you. This one I have a typo. It should be GM2 over GM1. I'm sorry. Thanks for catching that. Yeah, because this is negative 1 over A. Yeah, very good. Right. So here I have A equals to negative GM1 divided by GM2. Okay, any other questions? Oh. Okay, I remove the whole thing. Should be 1 plus GM2 over GM1. Okay, and let me just don't put this, that will be confusing. Okay. Okay, good, thank you. So let's yeah, when it should be okay. Yeah, any recording will be there. Okay, now then the next thing I want to know is what is the input impedance of this device, right? It looks very complicated, but now can you just apply what we have learned before? How do you find the input impedance by definition? What do you do? Do not nervous, right? Just step by step. Now you are in the test bench. I want you to find the input impedance. What will you do? Find the resistance. How do you find the resistance? Apply a voltage. And then? How do you find resistance? You apply a voltage and then what? Measure the current, yes. Yeah, maybe it's too easy. That's why you dare not to answer, right? But Yeah, sorry for that, but this is very important. You write this down, then you can do it. Otherwise, you get scared by this circuit. You just don't know where to go in, right? It's so complicated. Now you say apply an input a voltage and measure the current. So you basically are saying that what is the current here. But there's one condition that you might forgot, but it should be in your cheat sheet. I out equal to 0. The output should be open by definition. Right? In this case, it doesn't have big effect because the input gate is infinite, right? I mean, not, yeah, anyway. Then, well, how do you find V in divided by I in? Which law do you use? Ohm's law, simple one, right? But without using Ohm's law, without setting KCL and KVL, you can do it by inspection also, right? Because I give you a resistor that is 100 ohm, one side connected to ground. I ask you, what is the impedance? Well, you can try to solve the KCL, KVL, come up with that. Oh, this is 100. Or you can tell me already, you give me 100 ohm. Yeah, it is 100 ohm, right? Why do I need to do the experiment again? So, what do you see when you go in? Yeah, the first thing I see is RS. Of course, I need to be very confident seeing that just by inspection is correct, right? Because if the RS is actually connected to another transistor source or whatever, that won't be so easy, right? But now I clearly see that this is just like a resistor in front of me on the test bench. And then it's connected to a capacitor connected to ground. Isn't that the impedance is just what? RS plus 1 over S, yeah, C in, or you can call it CGS1, just the whole thing, right? 1 over the whole capacitor, if you want. CGD1 times 1 plus GM1 divided by GM2. It's difficult to see. Is this okay? Sorry for that. Let me rewrite it. Right, but is this okay? Any questions? Is this clear? Trivial? Right, I just copy the whole capacitor, CGS1 plus CGD1 times 1 plus GM1 divided by GM2. Okay? It's too easy, right, that you think it is strange. But the good thing is that now you see that because GM1 divided by GM2 is approximately equal to 1, I don't have a big Mueller cap. So the pole here, I mean not pole, the impedance here, right, have a small capacitor instead of a large one. Okay? Now how about the output impedance? What do we do again? By definition, what do you do? You apply the voltage at the output over the current, right? And under what condition? We in USL, very good. So now you don't need to bring your cheat sheet. Other people need to. So I'm going to ground this guy. I look at and I need to be careful. I need to look at here, I out, right? And then look in it. So from this, again, you can do small signal, but you don't want to waste time on this, right? You will do that in the first class of 124. But now you're almost graduating. Then tell me what is the impedance that you will see? You're an electron, you keep walking, what do you see? Okay, first you see a path like this, but this is a branch only, right? So it's not the total output impedance, right? You still keep walking, and then what do you see? Common source with degeneration and RL, right? So you have three paths, right? They are all in parallel. So I can say that this is equals to RL parallel what you just said as CGD2 plus CDB2. Then the whole thing parallel the common source with degeneration. But then I will try to save my time. I say low channel length modulation. And I know that common source with degeneration is just having the R0 multiplied by GMR0, right? So infinity multiplied by infinity is still infinity. So this is like infinity, right? Because this is really large. So it is dominated by RL and this capacitor. Why this is important? Because now you have this insight. If you want to do impedance matching, then you will try to change your RL and this parasitic, right? And you will see that at low temperature, this is not important. But at high temperature, low frequency. At low frequency, this is not important, right? But at high frequency, this becomes important. It can be very small, and then you screw up your output circuit, right? Yeah. So I think that's all I want to say. Okay, so I think we are done with the Cascode. Any questions? Now, if no, then we look at the differential amplifier high frequency response. Oh, now it will be very interesting, right? We're going to spend how many transistors we have? Oh, only two actually, but we can have this have two also, right? And then we have 4 capacitors and 2 resistors. It's almost impossible if you try to solve KCL and KVL, right? But the good thing is what? Because it's differential, because it's small signal model, and also because of what? Absolutely symmetric. I actually forgot. I'm not trying to test you. It's absolutely symmetric. Then what can we do? Yeah, we can make half circuit analysis and also do virtual ground. Once I do this virtual ground, what type of circuits is this? Look at it carefully. Ground, input to the gate, output to the drain. What circuit is this? It's common source. And we spend a lot of time to study common source already. And these are the equation. You can just apply them directly. Right? This is the full set of equation. Remember, we instead of finding the poles, right? This includes the zeros. And what I'm trying to say is it is just the same as common source. So if your circuit is limited by something, this differential amplifier will be limited by that one. For example, you are limited by the pole, which is due to the Mueller cap of CGD. This will have the same problem. Now, if I try to change it to a differential pair of Cascode, a Cascode circuit with in differential pair, or Cascode differential pair, remember that one? We have learned that, right? If you forgot, let me draw it. It is just, right? I just assume I have ideal current source. We studied that before. We in one. V into, this is V out. Is this okay? This makes sense to you? A differential pair. The left is a Cascode circuit, right? The right is also Cascode. Again, I can use virtual ground. So this is exactly the same as this one, right? And in that case, you don't have the Mueller cap problem because, again, it's only increased by 2 times. Okay? So this line is easy. because all you need to do is just repeat what you've done before by using virtual ground. Okay, any questions? Okay, if no, then we will